to do. When I worked things out, it looked like we could be finishing up early April with the required materials and leaving us, the rest of April. Well, there's a spring break in there, so don't go to do review in some of these extra supplementary topics that I would like to do parts of, at least. So 7.1 is technically one of those topics, but I think it's a good one to do because I'm pretty sure that this technique is going to crop up inside of things that we're going to do in Chapter 9 in the textbook. So I want to do this here and now so that we can at least be familiar with this technique and use it as it comes up kind of organically rather than having to oh, nope, never mind, that homework problem you couldn't have done because you needed to be able to do blah, blah, let's just do it because it's not a big deal. Okay? Okay. So the idea here, we saw earlier that U substitution was basically our process for doing the antiderivative of a chain rule, right? It's basically running the chain rule in reverse. Today, we're going to talk about integration by parts, which is going to be our tool for running the product rule in reverse. Kind of. So remember from the product rule that the derivative of f of x times g of x is f of x times the derivative of g plus g times the derivative of f. So if I integrate both sides, I know that the derivative cancels with the integration, so I just get f of x times g of x. And then I would integrate this side. Howdy. I can then distribute that integral to both places. And then I'm going to subtract this integral to the other side. And what we have here is our formula for our integration by parts. Now, typically we write the rule, every time I've seen this written in a textbook, we write it with u's and v's. So we'd say this is the integral of u times dv equals u times v minus v times d, or integral of v times du. Okay, so that's our integration by parts rule. And from here on out, all we're going to do is kind of run through a bunch of examples to talk about how we choose what function to make u and dv, and then some of the sneaky things that can kind of come up and how we can adapt this to work for a definite integral. But this is the big idea here, is this formula, which is just a consequence of the product rule integrated and rearranged. So as I mentioned, choosing the function for u and the function for dv is going to be the trickiest piece here. Typically, we want to choose u so that when we take the derivative, we get something simpler. And we want to pick the dv to be a function that we can integrate easily. So if I look at this first example here, we have x times sine x. So my two functions are x and sine x. If I use my rule that I want to choose u so that the derivative of u becomes simpler, which function would I want to choose for u, x or sine x? I want something to get simpler. What should u be? X, right? Because the derivative of x is just going to be 1, so du is just going to be dx. Is everybody okay with that? So that means that dv then, it needs to be sine x dx. So if I integrate that, that'll allow me to get v. So the integral of v, or of sine, is, the antiderivative for sine is negative cosine. And now I have all my pieces, right? So I have u, I have du, I have dv, and I have v. So I'm just going to put this all together now into my formula. So I have u times v plus the integral of v du. So this problem then just turns into doing the antiderivative of negative cosine. The antiderivative of negative cosine is? Well, the antiderivative of cosine is negative sine. So negative of a negative is going to be positive sine, yeah. And then what do I still need? Plus c. Excellent, yeah. Good job. Let's do another example. So this one, hopefully, really obvious what we should pick for u and dv, right? So one thing is the natural log of x, and the other thing is just, hello, computer, what is going on? OneNote, or did you break? I think you might have. That's always, oh, did that? Oh, I think it did it. Finally caught back up. OneNote, you booger. Sorry about that. Okay. So we have just two choices, right? We have natural log of x and we have dx. Everybody's okay with that? So u is just going to be, which one of those do you know how to differentiate? The natural log of x. How do you differentiate dx? I don't know. And then dv is just obviously going to be then dx.
But like, isn't that just like a normal?
What's the antiderivative rule for the natural log?
It's just like, well,
No, the antiderivative of 1 over x is the natural log. We don't have an antiderivative rule for
right,
the
yeah,
natural
yeah.
log. Yeah, right? So like, what do we do with that? Integration by parts. So the derivative of u is just going to be 1 over x dx. And the integral of v is just going to be x. Everybody's okay with that? I didn't really write any symbols because those are both pretty easy things to do. And now we're going to go ahead and write our formula. So I have u times v plus the integral of v du. Or I'm sorry, integral of v du. And whoa, look what's happened to that integral on the right-hand side. And Mr. Kulik, what are you doing here? Look what I did. What symbol is supposed to be there?
So what I got that? So like that is.
So the idea here, Blake.
Going back, can you go back up to that formula real quick?
Yep.
Okay, so I just wrote it wrong. Never mind.
Okay.
These and these are mixing.
Yeah.
They're too similar.
Yeah, I know.
It's just the example before.
Did I screw up the negative sign there again somewhere? There we go.
And then what is the antiderivative?
Why are we, like, this OneNote is just like trying my patience today. No, I think that I think that's still correct. Okay, come on now, computer. So the antiderivative of cosine is positive sine, right? Well, the antiderivative of sine is negative cosine. And then the antiderivative of cosine is positive sine. Because if I differentiate, if I take the derivative of sine, that's just regular cosine.
Yeah.
Right? So the antiderivative of cosine is just regular sine.
Right, but before it was.
We did the antiderivative of sine was negative cosine. Which is right, because the derivative of cosine is negative sine. Right? Is it, we okay?
Yeah.
I know, I get them goofed up all the time too. It's easy to do. All right, back to this one. The good thing is, look at the side of this integral. Look what's happening. X times 1 over x. Gonzos. That's lovely. So what's the integral of dx? Just x. And then I still need my plus c at the end. So the lovely part about this integration by parts, again, is it's taking an integral that's really difficult to do and turning it into a function minus some integral that's hopefully easy to do. Okay. Next one here. Again, we have the product of two functions. I see the t squared, and I see like e to the t. Which one do we want to make u, and what do we want to make dv? We're going to make u what? Does that get simpler when we differentiate it? Doesn't get simpler. Which one does t squared get simpler as we differentiate it? Because the exponent gets smaller, right?
Yeah.
That's what I would do. Yeah. Because eventually, if you have to do parts more than once, like eventually that t is just going to go away. Right? If you have to do integration by parts more than once, which is what we're going to have to do in this problem. If you did it the other way, you're going to be stuck. It's just going to get more complicated as you go because you'll have to integrate t squared. So you get something t to the third over 3. And each time you run integration by parts, your exponent's getting bigger. Which is bad news for us. Just leave it that way, right? And the antiderivative of e to the t is just e to the t, right? So we have u times v minus integral of v times du So I notice here that I can take that 2 and pull it out front, right? But the integral that I'm left with, still don't know how to do that. But what did you notice about the variable term? The t squared has now become a t, right? So what we're going to do, we're going to do another integration by parts here. Because the next time we do this, we're going to be left with just e to the t. So I have all that stuff, the t squared e to the t minus 2. And then when I do that integral, I have u times v minus the integral of v du. And that's now an easy integral to do. What's the antiderivative of e to the t? Just e to the t. So you can see that in this kind of a situation, if you have like an exponential or a trig times a polynomial, you might need multiple integration by parts, each time whittling down a little bit off that polynomial until you end up with just the dx or the dt or whatever it was. In which case, at that point, your integration by parts would be able to stop because you could be left with just exponential or trig or whatever that you can do. Now let's look at this one. This is quite tricky. Why is this tricky? Right, yeah, so like if I look at e to the x, if I take the derivative of that, I just get e to the x, that's not simpler. If I take sine x, I do the derivative of that, I get cosine. That's not any simpler. So like neither one of these is going to be getting simpler. So we're going to have to be a little bit clever about what we do here. So we're going to pick a value for u. And I think in this case where you have two things that don't really get simpler like this. You probably want to pick the exponential as your u. Although in this case, it might not matter which one you picked as which. So the derivative of u is just going to be e to the x dx. And the integral, or the antiderivative of sine, is negative cosine. All right. And we can see right away that, well, u times v minus the integral of v du does not really help us out any, right? I'm going to go ahead and come on. Like, I just don't get it. Why are we being such a... There. But that doesn't really make life any easier. What do you suppose we're going to do? Let's try it again, right? We've seen that sometimes that'll work. So I have that.
Oh, well, yeah.
The antiderivative of cosine is positive sine, yeah. I know, it gets me all the time too. So I have u times v minus the integral of v du. And oh, something wonderful has happened here. Let me zoom out and see if you can notice. It's subtle, but it's the answer to our prayers.
Well, I mean, it just returned back to the same, like we just found the exact same problem inside of it.
Mm-hmm. So guess what I'm going to do now? Going to add that to both sides. So I have 2 e to the x sine x dx is equal to negative e to the x cos x plus e to the x sine x. And then if I just divide both sides by 2 and tack on my plus c, there's my answer. Right? How sneaky was that stuff? So what's the takeaway? If we can run this integration by parts so that it cycles back to whatever we started with, that's our cue that we're done, because we can just move that back to the original piece and then divide by the constant and boop, got an answer. Right? Mr. Kulik, that was some sneaky crap right there. Was not expecting that. Would not even come up with that on my own. That would have not occurred to me as something to do probably ever. Super sneaky. Haha. I love it. All right. So if we want to do the integration by parts with a definite integral, works just like we would expect, right? We evaluate, the bounds of integration become the evaluate for the uv, and then the bounds of integration for the integral v du. So let's do another example. Here, what are we going to pick for our u? X?
Probably.
Dx is our u?
Inverse arctangent.
Yeah, inverse tangent is like the only choice because we don't know how to differentiate like a dx. What is the derivative of dx? I don't really know. Is that a thing? I don't think it's a thing. So this is like the only kind of way to set this up, is the dv has to be the dx. And then the derivative of tangent inverse is 1 over 1 plus x squared dx. And let's change our bounds of integration here, might as well, right? So tangent inverse of 0 is? What angle gives you a value of 0 for tangent? Think about what the graph of tangent looks like. It looks like...
But isn't that what like tangent looks like, not what
right.
like inverse?
But that tells you if theta equals 0, tangent theta is equal to 0, right? So if we know tangent theta is 0, the angle for theta is 0. Where is tangent equal to 1? What angle is tangent equal to 1 at? Pi over 4 is correct. 45 degrees. Pi over 4. So then I have tan inverse x times x evaluated from 0 to 1 minus the integral from 0 to 1 of v du okay. Here, tan inverse of 0, tan inverse of 1 we said was pi over 4 times 1, and then minus tan inverse of 0 times 0. Okay. So there's that. How are we going to do this other integral over here? It's one that we've done before. I would just do this with u sub. What would we pick our u to be? 1 plus x squared. So du over 2 is equal to x dx. Oops, that's not what I want. So u of 0 here would be 1. U of 1 would be 2. And what's my antiderivative for 1 over u? The natural log of the absolute value, u, evaluated from 1 to 2. So that's the natural log of 2 minus the natural log of 1. So you could either think about this using the quotient rule, which would be the natural log of 2 over 1, or you might remember what's the natural log, or any log of 1? 0, right? That's what I would think about here. So we have pi over 4 minus natural log of 2 over 2. And there's no c here. Why not? It's definite. Yeah. What do you guys think?
U's that we found.
I didn't mean to do it.
Okay, so that was.
Yeah, this right here, we didn't need. Shouldn't have done it. Yes, excellent. I was going to get back to that. We're going to skip doing that in the interest of time. And the assignment here is just 3 through 17 odds. It's going to be just like the examples. So you're just going to be doing integration by parts. There's no story problem. There's no context. It's just like do the procedure. So far, so good. Okay. And I'm going to start 9-1 today also. So in chapter 9, we're going to be looking at differential equations and solving differential equations. So when we talk about a differential equation, it's going to be something where a derivative is equal to some other function. And to solve it, we're going to want to find the equation that gives us that derivative. That's kind of what we mean by solving. So the kind of the natural place to start here is to talk about population growth as kind of a differential equation situation that is relatively easy to conceptualize. Paul? Sure. So when we talk about a population growth model, the two variables that we're going to be measuring is going to be time and population. As population tends to grow over time. So the first model that we're going to look at is just an exponential differential equation. We're going to just assume that population grows at a rate that's proportional to the size of the population. So if you have like two populations that grow or that have different sizes but grow at a similar rate, you're going to have more population grown in the bigger or more population increase in the bigger population than the smaller one, because it's, like 5% of a million is more than 5% of 10, right? It's kind of all we're saying. It's proportional to the size. So our basic differential equation for this is just dp dt equals kp, where k is just some constant. Remember, p is our population, so we're going to assume that that population is non-zero, because if you don't have anything, it can't grow. And that the population is always going to be non-negative. I should say positive, right? So even as you go into the future, it's never going to like, whoop, and just become zero or negative or something. So assuming that the k value is positive, then our derivative, dp dt, is also going to be positive for all t. Why can we say that? Well, because p is positive, right? So you're always going to be adding. Okay, so this is going to imply that the population is always increasing, right? Because the derivative is always positive. And as the population increases, so does the rate of population. Because the rate is k times p. So as the p gets bigger, the rate of population growth is going to be bigger. Everybody kind of see that? Okay. So can we think of a function whose derivative is a constant multiple of itself? What do you guys think? Well, not x squared. Yeah, e to the x, right? That's what we're looking for. I'm going to write it as e to the t, though, since t was our variable, our independent variable. So if we consider like all possible solutions to that differential equation, dp dt equals kp, we have something like this, right? So these are all, each of these curves represents a different equation whose derivative is dp dt equals kp.
How can we look to decrease?
Well, because we've yet to think about the constraints on k.
Okay.
So, but we said that the population can only have positive values, and time has to be positive. So our possible solutions are actually just starting at the positive x-axis, or starting on the positive x-axis, so starting here, and then only the things in the first quadrant, right? And then why do we have like a series of these things that are kind of like all parallel to each other, but like stepped up like this?
It's because that's where the starting population is.
Because it's like plus the constant, right? You have like e to the x plus 7, e to the x plus 4, e to the x plus 9. All of those give you the same derivative, but they're different functions. That's why we have all these possibilities kind of drawn in here.
The starting point, it changes the rate at which the curve is taking. I think if you start higher, it's going to increase faster.
Right. And you can kind of see that here, like the red piece, if I look at the beginning, that slope is not nearly as steep as like the black slope is, right? Okay, So what kind of conditions would this be appropriate? So usually we say ideal conditions. That means you have like an unlimited environment, adequate food supply, absence of predators, immunity from disease, etc. Basically, we're eliminating all the normal things that we know populations are susceptible to. In reality, any or all of these things really become a limiting factor to population growth. So we call that upper bound to a population its carrying capacity, and we use the letter M to represent the carrying capacity. When the population is relatively small, ideal conditions are basically fine. It's appropriate, right? If you have all of North America and you have like 17 people, like no problem. You can act as if we have ideal conditions, like there's not a lot of, if you're packed to the gills with people, no longer appropriate. But if you have a small population and a big environment, usually that's okay to just think of it as the ideal situation. So the second model is going to be where we try to take some of these things into account. So we call this the logistic differential equation. In this sort of situation, the rate of change of the population is approximately Kp when P is small, and the rate of change of the population is negative if P ever passes that carrying capacity. So if we kind of incorporate these two assumptions, we'd get a differential equation that looks like this, that dP dt is equal to Kp times 1 minus P over M. So if P is small, the fraction P over M is basically, if P is small, the fraction P over M is basically 0, right? Because M is the carrying capacity, that's going to be a big number. And if that's 0, then you just have 1 minus 0, which is just basically Kp, which is getting us this first condition, right? If the population is small, we're basically just Kp. Now, what's going to happen if P is bigger than M? If P is bigger than M, what does the fraction P over M become? Bigger than 1. 1 minus something bigger than 1 gives us a negative number, giving us a negative growth rate for the population. This appears to cover both of the two things we want this model to do, right? Act like ideal conditions when the population is small, and give us a negative growth rate when the population exceeds the carrying capacity. Does that feel good? Okay. And we talked about these two. So if P, what if the population is equal to the carrying capacity? What if P is M? So the growth rate becomes 0, right? That's what we call an equilibrium solution, as the growth rate just becomes nothing. And then if our P is between 0 and M, growth rate is going to become positive because you'll have a fraction less than 1. And if we're bigger than M, we talked about that, it becomes negative. So what we have is something like curves like this, right? Where we have two equilibrium solutions, one where the population is 0, because if P is 0, then this whole thing is 0, right? Everybody agree with that? And then we also have an equilibrium, a situation where P is M, because this thing would then be 0, which makes the whole thing 0. Is that okay with what we're talking about? So again, this picture is a bunch of possible solutions to this differential equation. Okay. Time to talk a little bit of vocab here. Notice we haven't really done any math yet, right? We've just kind of talked about like what a differential equation is, given some examples of like how we build them based on like real life situations, right? We haven't talked at all about solving one or anything of that nature yet. Okay, so some basic vocab. A differential equation is an equation that contains an unknown function and one or more of its derivatives. For example, the derivative of y is equal to xy is a differential equation, right? The order of a differential equation is the order of the highest derivative that occurs in the equation. So this one is a first order differential equation because the biggest derivative is the first derivative. Everybody's okay with that vocab? A function f is called a solution of the differential equation if the function is satisfied when y equals f of x and its derivatives are substituted into the differential equation. So if y is equal to f of x is a solution to y prime equals xy, then the derivative of f should give us x times f of x, right? Which is just xy. Is okay there? To solve a differential equation, we're going to be expected to find all the possible solutions of the equation. And we've done this a little bit already, right? So if I have the differential equation y prime is equal to x cubed, well, what's the solution to this differential equation? We just integrate both sides, so the y prime becomes a y. The x cubed becomes x to the fourth over 4, and then we tack on the plus c at the end. So that would count as all the solutions to a differential equation. How is this different than the things we've done before? It's not really different yet. It's not really different yet. And that's okay. That's good, right? I like it when it's kind of like, okay, you're just giving everything a new name, but if everything is still the same, I can do that because I could do it before. I just need some new names. That'll do. All right. Let's look at some examples now where we actually do some practice. Says, show that every member of the family of functions, yada, 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 is a solution of the differential equation y prime is equal to 1/2 y squared minus 1. How do you want to do this? Well, based on before, what it says is all I should have to do is take the derivative of this and make sure it looks like that. Right? Okay. So what do I need to use to take the derivative of y with respect to t? Maybe we'll write it as dy dt, so it's like super clear that t is the independent variable there. How do I take the derivative of 1 plus c e to the t over 1 minus c e to the t? Quotient rule, very good. How do I do the quotient rule? It's the top times or the bottom times the derivative of the top. But yep, and then minus the top times the derivative of the bottom over the bottom squared. Everybody so far so good? Okay, so let's go ahead and do some simplifying. So I'm just going to take that c e to the t and just kind of factor that out. And then this negative and that negative are going to just turn into pluses, right? Everybody's okay there? So that's probably where I'm going to stop here. Unfortunately, that doesn't look like this, right? What I think I'm going to do now, that I think will make life easier, oh my goodness, is I'm going to go to the derivative now. And see if I plug that in, since I know what y is. If that'll simplify down to the same thing I have over there. That feels easier than trying to keep hammering away at that derivative I just found and trying to make it look like 1/2 1 minus y squared. Is it'll just work a little bit on both and meet in the middle. Okay, so I'll square that thing. And actually, I'm probably just going to write it this way. So we'll make a common denominator. With the 1. Everybody's okay what I did there? Okay. Now I just think I need to FOIL some stuff out. So that's going to be 1 plus 2c e to the t plus c squared e to the 2t minus 1 plus 2c e to the t minus c squared e to the 2t, and all of that stuff is still over 1 minus c e to the t squared. So that stuff all cancels. You have 4c e to the t. Still have that 1/2 out front. And that's wonderful. Now I got them to they're the same. Was a little rusty on their quotient rule. It's okay.
I think one of the questions in the AP,
Yeah, I think so.
I kind of guessed on which one was the derivative.
Okay. So here it says find a solution of the differential equation that's given above that satisfies the initial condition y of 0 equals 2. Okay. So what do we need to do here then? We know that my solution is in this form, 1 plus c e to the t over 1 minus c e to the t. We're basically asking then, what is the c? If I know that y of 0 should equal 2. Well, okay. I'll just plug in 2 for y and 0 for t. So I have 2 is equal to 1 plus c over 1 minus c. How do I solve that for c? Multiply by both sides by 1 minus c. And then I subtract 1 over, and I add 2c over, and I get that c is 1/3. So that's everything I need. So that will do. Is that the way Mr. Kulik would write his final answer, though? No. What does Mr. Kulik hate about this?
There's like multiple fractions.
I got fractions inside of fractions, yeah. Here's what Mr. Kulik would do. We're just going to multiply the top and bottom of that fraction by 3.
Is this required? Would this be required on the AP test?
Uh,
In order to get a final answer like that.
so if this is a free response question, no.
But if it's a multiple.
If it's a multiple choice, I guarantee you that's the way they write it.
End of this period one, everyone from the high school, you're gonna head to your community time room, quickly head to your community time room, and then we will be dismissed for math. So if you need to use the restroom.
And
use
look at
the
this
restroom,
timing.
community time,
Wow.
And at the end of this period, everybody goes to community time and waits for the direction. Thank you.
You're welcome, Miss Anderson.
How many pages of, like, how long is the bio?
So this was pretty quick and easy.
How long did it take? 'Cause I feel like I didn't do all of